So I'm Megan. I'm an associate research scientist here at Flatiron, and I have used MCMC a lot in my research. I wouldn't say that I'm the leading expert on MCMC, so we'll all kind of muddle through this together this morning. But I do know quite a bit about the practical applications of it, so that's what I'd like to kind of focus on this morning. And if you have any really difficult questions, I might just punt them to Dan Foreman Mackey later, because he pretty much literally wrote the book on MCMC for astronomy. So luckily we have many local experts here. So to start off with, MCMC, this stands for Markov Chain Monte Carlo. And there's two components to this, Markov chains. So we'll be talking about Markov chains first, what they are and what kinds of special statistical properties a Markov chain has. In essence, a Markov chain is a sequence of stochastically generated numbers that follow certain rules. And we'll get into that a little bit more later. The second half of this is Monte Carlo, which is a place that people go to gamble. And it becomes a shorthand, kind of, in math and science for random samplings, random generation, because of the gambling metaphor. So Markov chain Monte Carlo is sort of a method that generates randomized samples that fall into a Markov chain, at least if you're doing it right. Your random samples in the end will have the statistical properties of a Markov chain. And specifically in this context, the numbers that we want to generate are going to be samples of parameters from a posterior distribution. And don't worry about all of the details. We'll be kind of breaking that down throughout the rest of this talk. But in general, MCMC is really widely used in astronomy and in the sciences in general because it's a powerful way of generating these randomized sequences of samples from the posterior distribution. So I want to start off with a little discussion question. So please turn to your neighbor and talk a little bit about whether or not you have ever used MCMC yourself or seen it used, and what was the scientific application? Like, what was the reason that MCMC was used? So take a few minutes to talk about that. All right. Sounds like things are wrapping up a bit. Can I have a volunteer or two to give me an example of MCMC and its applications? Anybody? Just pop up your mic. Nope. Rocio? May I call on you?
Okay. Hi. So I was remembering one example we did in class, that it was a magnet and you had all the spins like a network, and the interaction between the spins was proportional to the magnetic field, and the way we study what was according to the magnetic field you were applying, the state of the magnet was with the Markov chain. All the interactions were that was a Markov chain. Yeah.
I see. So that's taking advantage of the fact that neighboring states are correlated with
Yes.
each other.
Exactly.
Yeah, okay. So a Markov chain can reproduce processes in nature, and we might want to take advantage of that when kind of fitting a problem. Anything else? Yes.
Okay. So I've used it before without really understanding what it was doing, but used it before in like a SED fitting, where it was with somebody else's code and then generated a corner plot and gone, oh, I have no idea what's going on. So, but having a lot of like free parameters that you kind of have to be able to pin down somewhere, it was a useful tool for reasons that I didn't understand at the time.
Right,
Might
yeah. I think
not
that's
still.
how the majority of people use it in astronomy, as a way of exploring parameter space and, as you say, generating a corner plot. So we're gonna come back to corner plots and what they are and why they're useful. But I've put down a few things just to throw them out there, and you may recognize some of these to problems that you have faced and maybe even things that you've seen people use MCMC to do. So one way to use MCMC is if you want a posterior distribution of your parameter space. So what I mean by that is we talked a bit yesterday about the basic principles of Bayesian statistics and the posterior distribution being sort of the expectation values of a given parameter. An MCMC is a good way of sampling the posterior, generating a bunch of samples of whatever parameter or whatever function of a parameter you're interested in that is naturally properly weighted by the data. And related to this, once you have the posterior distribution of something, often you'll find it looks like sort of a nice Gaussian distribution. There's a couple interesting, useful things about the Gaussian. One is the mean of it, which is your expectation value for the parameter. So in some sense, it's your best guess at the solution. But the thing that MCMC is really good for is giving you the entire posterior distribution, which includes an estimate of the uncertainty on that parameter based on the width of the posterior. So if I had, let's see, I'm going to try to use this. If I had a posterior distribution where I have some parameter theta that I'm interested in, and I want P of theta, the probability distribution of theta, and my MCMC can give me, I claim, this distribution. That tells me not only the best value of theta here, but also the range of thetas and the probability that you could have. So this is a probability density function, and you can use it how you would normally use it by integrating under this curve to tell you the likelihood that your parameter lives within, say, any given region of the potential values of it. So an MCMC can be really useful for giving you uncertainty estimates, because you can say go from your standard definition of a sigma or 2 sigma or 3 sigma and calculate those percentiles and integrate between the two to give you sort of the range of parameter space that you have some sigma certainty that your parameter lies within. So this can be This can be a widely used application. Another related thing is you don't only get the posterior distribution of a given parameter, you're also exploring the entire parameter space at once. So when you have a model that has several different parameters that may depend on each other, you can see if you're exploring parameter space and you change one parameter, what does that do to the likelihood of the other parameters? And so we'll go into a little bit of an example on this in a bit, but the exercise you were doing yesterday with fitting a line to data was one example here, where the slope and the intercept are correlated parameters. And by using the MCMC, you can really visualize that and see it and marginalize over it. And finally, this one is a bit of a more advanced application of it. I think I most often see people using MCMC in the literature for uncertainty estimation or for exploring parameter space. But you can also use it to calculate Bayesian evidence, which is when you need to explore all possible parameters and integrate them up to see how likely your model in general is to fit the data. So it's really hard to effectively explore all of parameter space, and MCMC can be a good way of doing that, of giving you a bunch of random places in parameter space that you want to sample to integrate over. So kind of a common theme in this is that MCMC gives you a posterior that can be integrated, and that's a lot of the applications. So I'll step back a second and go back to this Markov chain idea. So a Markov chain is a stochastic process where we're going to have a set of numbers, let's call it x, and this is just a sequence, x0, x1, dot, 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 xn, xn plus 1, etc. So this can be any stochastic sequence or chain. It just has some randomness in it. What can make it a Markov chain is when x of n plus 1 depends on the value of x of n, but it doesn't depend on anything else prior to that. So this is saying that I can have a set of sort of transition probabilities between different states that will tell me how likely it is to go from x of n to x of n plus 1. And it doesn't have a long memory of what things came before. It only cares where are you sitting now, what's your current value of x, and what does that mean in terms of the next value of x that you're going to draw. So one thing that we sort of need to know here is the probability of going from x of n to x of n plus 1. A subset of Markov chains have some other nice properties, and we're going to insist on having these particular properties for the MCMC. So this is the thing that makes it Markov is that dependence on the previous number and nothing else. But there can be some other things as well. So the Markov chains that we're going to use for MCMC, we want them to be stationary. So that's saying that probability of going from x of n to x of n plus 1, it doesn't matter if you're here at x of n or if you initialized the chain here at x of n. Like, this is kind of related to the idea that that you don't have a memory of where the chain has been. This number is going to be sort of a constant throughout the whole chain of values. So that's a stationary thing. And the special subset of Markov chains we're going to be using also have a reversible property. So they're time invariant. That means that in this case, you would also say that the probability of going from x of n plus 1 back to x of n is symmetric. And that's not required of all Markov chains, but as we'll see, in order to estimate the posterior with a Markov chain, that property needs to hold. So this is a little bit abstract. Let's do an example of what a Markov chain looks like, just to get a better sense of this to start with. So by popular request, my example is based on a dog. This is Oscar. He is my friend's dog and sometimes stays with me. He is a dog of very little brain. His head is about this big, and I think it's like 90% fluff. So what Oscar cares about most in the world is when it's going to be time to go for walkies. And because he has very little brain, he doesn't really know that much about like schedules or time of day or what actually matters. His model, as far as I can tell, of when it's time for walkies is, did we just go on a walk? If not, maybe it's time to go on a walk. So let's say that Oscar measures whether or not he is on a walk, if he's in state A of happy walk time or state B of sulking because it's not walk time, about once an hour or so. So Oscar has measured this in his tiny little brain, and he has decided the following probabilities. If we're on a walk now, then probably we unfortunately won't be on a walk right after this. So the probability of going from state A to state B is 99%, leaving a 1% probability in very special circumstances that we go on a walk twice in a row. Meanwhile, the probability of going from state B to state A is, let's say, maybe 15% of the time we transition from not going on a walk 1 hour to going on a walk the next hour. And again, B to B is then 85%. So we can take this as a two-state Markov chain. And I'd like to take a little break for an exercise here, which is this website. For those of you who have laptops out, this website is a very fun demonstration of what Markov chains look like. And, and if we go down to this example here, this is the state A, state B sort of example that we were looking at, and you can change these probabilities. So why don't those of you who have a computer out go to this site and do that, and sorry. All right, there we go. So here's the website. So try putting in these probabilities and make a note of what sort of chain is produced by doing that, and see if that looks like the chain that you might expect. Yeah, so the probability of going from A to B should be coupled to the probability of going from A to A because there are only those two options. If you're on A, either you're going to B or you're going to A. So those two should sum up to 1. I think that should be how the sliders go.
Well, it's coupling probability of A to A to B to A.
No, this is saying if A, go to A. If A, go to B. So those should be coupled because that's A to B, A to A.
Yeah, so. Right, yeah. So I was using, I was using a different notation here. So this is sort of given A, go to A, or given A, go to B.
Could you go back to the doggy so we
Yeah. Sorry.
Thank you.
Okay, so can someone who has this working read out to me a sequence of what this is doing in time?
You mean like A, B?
Yeah, exactly.
Just as it's doing it?
Mm-hmm.
Okay, so.
You can slow it down.
How fast can you write? Yeah, I will put it on the so B, 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 B.
Poor Oscar.
B, B, holy. B, this poor dog, B again. A.
Yay!
B,
Oh.
B, A,
Yay!
B,
Okay,
B.
great. Thank you.
This poor dog.
All right, so this is maybe not exactly what you would expect, but it, yeah, true. That's true. Yeah. So maybe this was overnight. We also never claimed that Oscar was extremely good at understanding the causality of all of this. So his model might not be perfect. But this has essentially captured the behavior of the system because you end up with long strings of not going on a walk for a few hours, followed by a walk, which is generally not followed by another walk. And so from this, we can take this sort of probability distribution of transitions and turn that into a stream of realistic looking data. In science, there are a couple of differences between this example and what we would generally do, what we would generally use a Markov chain for in MCMC. So one difference here is that we were using just a simple two-state system of walk or not walk. But generally, the parameter space that we're interested in exploring and the data that we want to predict are both continuous systems. So a Markov chain can deal with this. The reason that I gave you these discrete states is because it's a lot easier to just simulate it. But we could imagine generalizing this. Instead of walk or not walk, it's maybe the number of steps that we've taken in an hour. And we would still be able to write down a probability function here. It's just that instead of being those two numbers of state A to state A or state A to state B, and the same for state B, we would end up with continuous distributions of given A, what is the probability of going to B, and given B, what is the probability of going to A. The other difference here is that we don't actually have those distributions most of the time. So we were assuming that that Oscar, the dog of very little brain, had already calculated for us sort of what the model looks like and the transition probabilities. And from that, we were sampling data of what he might observe. But in the general case, we actually have the data, and we want to reconstruct what is the likelihood of one thing relative to another in the parameter space. And what does that mean about the model that is giving rise to the data? So Markov chains can be used in this context, but instead of defining our Markov chain based on a known probability distribution and going forward from there, we're going to introduce this Monte Carlo aspect, where essentially we're going to randomize over many different possible relations between parameters and see what fits the data best. So this is what the MCMC is essentially doing, is trying to generate a Markov chain based on kind of unknown transition probabilities that we want to figure out based on the data. So I'm going to go through a little bit of an example now in terms of fitting a line to data. And this is something that you were working on a bit yesterday. So let's say that I have some data in X and Y, and they look something like this. And I would like to fit a line to them. So we expect that we'll get something like that. And it can vary a bit, but there will be a strong covariance between parameters, because if I increase the slope of the line, the best fit will sort of pivot around the middle here, and so the intercept will decrease, and vice versa. So this is an example of kind of a correlated parameter space. And I'm cheating here because we can just see by eye that this is correlated and something of the properties of it. So I'm using this as a simple example because we have really strong expectations for what our MCMC should be spitting out in terms of the posterior distribution of this problem. In general, we're not necessarily going to know all of this, and we might be using the MCMC a bit more blindly, but it's useful to kind of look at where and how the MCMC works. So we're able to write down a likelihood of the data given the parameters. We can write down sort of a goodness of fit of this line by taking our parameters M and B, calculating what our predicted value is, what the green line is for a given M and B, and what the distance is between that line and the actual data, and that gives us a goodness of fit. So if I wanted to, what I could do is just take a bunch of different values of M and of B. I could sort of grid this up, and I could calculate at any given M and B, what is the value of the likelihood function. So I could go through and just calculate for lots of different M and B's, what is the likelihood here. And let's pretend that I've done that, and I've got the following likelihood contours here. So this is the region of the highest likelihood. This is the region of decreasing likelihood, etc. And out here, the likelihood is quite low. And I realize now that I've made the contours sort of tilt, but please pretend that I didn't. So what this is telling us is, as we expect, M and B are correlated parameters between the two. So what we'd like to do is, let's say we want to measure the slope M, and we don't really care about what the parameter B's value is. What that means that we want to essentially marginalize over B. And so the idea here is that if we were to just take a given value of B and say, what is the probability distribution for M, we could slice through like this, and we would end up with a PDF where M is like this, kind of low. But this isn't all of the information or the complete PDF of M, because if we had chosen a different value of B up here, we would be slicing through this instead of this, and so we'd end up with a distribution of M that looks like this. In order to get the full marginalized probability of M, what we actually want to do is try all different values of B and superpose them, weighted by the likelihood of B. So we want to use the fact that we know that the likelihood is high here in order to kind of weight these slices through the middle here up, and we want to weight the slices that only go through lower likelihoods down. So this is pretty complicated, but there's a shortcut to doing this, which is if we had representative posterior samples from this, where the samples follow the likelihood distribution so that they're mostly here in the highest likelihood with a bit farther out, then all we would have to do is make a histogram of these samples in either direction. And we would naturally end up having most of the samples fall in the middle here of M and decreasing out to the sides, and we would get sort of this nice posterior that we are expecting. And so here, when we've collapsed this on B, we've sort of naturally done this weighted sum because our samples are representative and weighted by the likelihoods here. Most of the samples fell in this middle region of B, where it's the most likely. There were less out here, and so we naturally got M mostly following this distribution. So essentially what we want to do with MCMC here is get that representative sample. And having that sample that goes through parameter space with the correct weighting based on what we know about the data will naturally give us both the shape of this correlation and the general behavior of the likelihood function through parameter space, And it will also naturally allow us to just make histograms or posterior PDF distributions of each of the individual parameters, naturally marginalizing over any of the parameters that we considered in the model, but we don't actually care about physically. So how does this work? How do I actually grab these random samples? It has to do with the fact that I have a likelihood. So if I were to just take any point from here, I would have an evaluation of how likely it is. It also needs a proposal function, which is often written as this Q. And so Q is analogous to, well, actually, so Q is going to be like if I have a given M and B, what is the next M and B that I want to try? And Q is something that we can choose for ourselves. So let's say I'm just going to assert that the Q that we want is a multivariate Gaussian. So that's saying that that with a normal distribution, I'm going to draw M from a mean of, okay, maybe the best thing to do is say that the mean is the previous point, and the standard deviation around the mean is something like, is sigma M, sigma B, where maybe sigma M and sigma B are kind of how certain we think that we will be on the slope and the intercept. And so if I have done this correctly, then I'm going to go into this this parameter space. I will drop something down here, and I'll say here's my sigma M for scale, here's my sigma B for scale. And if I were to draw something completely random from here, it might look something like this. So I'm going to go in here. I'm going to evaluate the likelihood at both of these points, and I'm going to use the ratio of the likelihoods between the 2 points to determine whether or not this is a good sample that I want to keep in the chain. So what I'm describing here is the Metropolis-Hastings algorithm that you were looking at yesterday. And just to put that up on the board, you can look at the side screens to actually see it. We're saying that we're going to go from one sigma or one theta parameter to another one by drawing a new random parameter, calculating the likelihood. So in this formulation, F is the posterior. It's the likelihood and the prior combined. So we're going to calculate the ratio of how well each of these samples fit the data relative to each other. If the proposed sample is much better than the previous sample, then I will say, yes, go to that. And so the chain that I'll end up generating is going to be something like, call that M0, B0, and call that M1, B1. The chain of thetas that I'll end up getting from my MCMC is going to be M0, B0, and then M1, B1, etc., off to the next point around here. If the random number that I had chosen was out here, where we said there's a very low likelihood, then the ratio of these two will be super heavily weighted towards just keeping this number. And so my chain will instead be the M0, B0, and then another entry that is M0, B0. We're going to keep sitting there, we're going to record it, and then we're going to try something else next. And maybe we'll try a better one and move. So the Monte Carlo part of this is that we're drawing a random new sample, and we're also injecting a little bit of randomness in whether or not we accept the sample. So those two extreme examples were like the ratio is above 1, the likelihood has gotten way better with the next sample, we absolutely accept it. Or the ratio is super close to 0, we really don't like the new sample, we're not going to accept it. But let's say it's in the middle. There's a very marginal increase or decrease in the likelihood going from one sample to the next. We want to have some random number that we've chosen between 0 and 1, that's the R in this formulation, that will determine whether or not we accept the next sample. And that's because if we were to always accept the next better likelihood, this wouldn't be an MCMC sampling the posterior, it would be it would just be an optimization algorithm. So we have, so we're using this algorithm to generate something that is a bunch of random points. And because of the acceptance criteria depending directly on the ratio of likelihoods to each other, we will naturally end up mostly sampling the high likelihood region here with a little bit out to the lower likelihood regions. And yes, occasionally we will go off into very low likelihood space, but that will be a very small number of the points. So in the end, we should actually end up getting this sort of likelihood distribution, which we can then collapse into different posteriors on different parameters and do with as we like. So, right. So one question here that might naturally arise is, well, we said that we were proposing a bunch of random things. Why do we bother re-recording the previous thing? Why not just keep the unique states that we've drawn? Because don't we want to explore the whole parameter space? Why would we just repeat what we already knew was a good solution? So the way to think about it sort of is that we are building up this histogram of the good solutions that we have. And so imagine that we chose this one really good solution and we very rarely, or we sat on it for quite a while. Maybe it's the no walkies solution and we just get stuck there for a little bit. If we were to only record that once, then it would just contribute like one little block to the histogram in M that we're making in the end. But because it is a highly weighted, very likely solution, we actually want it to contribute a whole bunch of blocks to this. We want it to be weighted with respect to the fact that it's a very likely solution. So hopefully that makes some intuitive sense. Yes.
Question here. If this like state has very high possibility, why will it be rejected? Like, shouldn't it like I keep like moving it around and like all the states I always get rejected and I always get the same point? I don't know whether this point answers the question or not.
Yeah, no, that's a really important consideration. So So yeah, we will probably stay on this point for a long time, but why will we ever eventually leave it if it's such a good state? And the answer to that is that random number that we introduced, the R term. So eventually we're going to end up drawing a random number that says, even though this next state that we've drawn is not as good of a fit, um, the ratio of the two states still goes above R, and so we're going to perturb the solution and go off of that best state. But we can end up in a situation of being sort of stuck on one point for long periods of time. And the way that that would look like if you're plotting like the steps in the MCMC and the value of m at each step, it would be like, okay, you're wandering around and then you just get to something and you get stuck there for a long time. And then finally you move off. And this is all the time that you're spending just sitting on there. And this can actually be a diagnostic of a problem in your MCMC. Maybe you're trying to make steps that are too large, and so you're getting a lot of things rejected because you're just trying to wander off into unrelated areas of parameter space. Or maybe the shape of your likelihood function is really weird, and you have like a super high peak here that has a kind of a like slope to it that is much higher than the rest of parameter space. And what you're trying to do is simultaneously well sample this peak area and also the broader parameter space. And so you kind of need different scalings. Yeah.
One thing I may want a little more clarification. So if I originally stay in P1, position 1, and then I move to position 2, which
Mm-hmm.
is kind of like get rejected, will my sequence be P1, P2, P1, or simply P1?
It'll be P1, P1. For every step, every proposal that you make, you record either the new state is the next step in the chain if it gets accepted, or the old state is recorded if it gets rejected. Yeah. Yeah.
And then kind of going off of that, a little bit more clarification, can you talk about the difference between MCMC and just optimization and like when you would want to use one or the other or pro
Yes.
con?
Yeah. So that's a very good point. So MCMC will end up wandering towards the likelihood maximum, and in that sense, it does optimize your problem in that it ends up at that region of parameter space. But it's not at all guaranteed to be efficient. And so MCMC is not really a good choice if what you want to do in your problem is optimize. It's much better for exploring around the region of parameter space that is the optimum. And to see that, you could imagine that instead of dropping our first point in the chain in this area, we had dropped it here. Instead of like an optimization algorithm might beelining over to here, we're probably going to end up like wandering around up here a bit, and then like eventually we'll start making our way here. And so that is not really an efficient use of your time, because the part of the MCMC that you're interested in is the part that achieves a stationary state of wandering around with equal probabilities throughout this part of the distribution. This is not really this part does not have the properties of a Markov chain because it's wandering in one direction as it goes through time, if that makes sense. So I'm actually running a bit over time here. Okay. I'll just quickly go through a little bit of practical considerations for MCMC. And I'm happy to answer more questions about this a bit later during the questions or during the break. Right, so MCMC in practice. So the example that I was giving you here, this two-dimensional thing, honestly, you don't really need MCMC to sample this. Fitting a line to data is a straightforward linear problem, and you can get an analytic uncertainty estimate for those things. But B, it's a low enough dimensional space that you could have just, as I used as an example in the beginning, you could have just made a uniform grid throughout parameter space, calculated the likelihood at each point, and used that likelihood weighting to tell you what the posterior is. The reason that we use MCMC is for the much higher dimensional parameter spaces where it just computationally wouldn't be feasible to grid up everything and calculate uniformly your likelihood throughout all possible combinations of parameters. MCMC is kind of an intelligent way of moving around the high likelihood region of your parameter space. And so in these contexts, MCMC can be really good, but it can also be a lot harder to implement than in this simple example, because you don't necessarily know a priori what sort of results you want to get in terms of your what we would call a pairs plot or a corner plot, which is the relationships between the 2 points. So I guess I maybe should have said earlier that if we were to make this into what we call a corner plot, we've basically made the corner plot already. What it would look like would be 3 panels like this. I'm going to call this so the corner plot would be, we're plotting all these samples in here, and so we end up with contours of the concentration of points that we get out of the MCMC. And then along this way, we're going to collapse this to be the, well, I guess actually usually, even though literally what we're doing is collapsing it along here, generally we're going to do it like that and like that. And so these will be the histograms for the values of M and B, just like marginalized over the other things. So this corner plot can be a really valuable output of the MCMC. I want to talk a little bit about like what kinds of diagnostics you might want to do to see whether or not your MCMC is working and is giving you the posterior, is giving you a representative posterior. So first of all, should you use MCMC at all? It depends on several things. So one is, as I was saying, the dimensionality of your parameter space. So if you have only one dimension to your parameter space, then don't do MCMC. Just sample a bunch of, do a bootstrap sample of different, or do a completely random sample of different values of your parameter and evaluate the likelihood there. If you have a lot of dimensions to your parameter space, MCMC is probably, in some sense, it's what you want, but it's not actually, the most basic MCMC will take a really long time to explore, say above 20 or so dimensions. And so Dan is going to be talking more later today about more intelligent versions of MCMC and related things that will be a better choice than basic Metropolis Hastings for this sort of situation. Relatedly, MCMC might not be a practically good thing to do if your problem takes a long time to calculate the likelihood. Because you notice that every time we were trying a new proposed set of parameters, we had to calculate the likelihood or the posterior at that, at the new parameter and at the old parameter, and take the ratio of the two. So if you're, say, trying to constrain the parameters that go into like a full-scale cosmological simulation, and you have to rerun the simulation with new starting parameters every single time in order to evaluate the likelihood, MCMC just isn't going to be practical for this, and you'll have to find workarounds. That being said, MCMC is still a really powerful tool, and so things like the Planck data, which do take a really long time to calculate the model, they have used MCMC, and they provide the MCMC chains as outputs in their large data releases because it's so time and computer intensive to produce those chains that they just make them available to us in general. So this is more of a practical consideration. All of these are more of practical considerations. MCMC could still be a good tool in theory, but it might not be easy to get up and running. Related to the point that Emily was making, MCMC is not what you want to do if what you really want is the optimum parameters. It is not a very efficient way of exploring parameter space broadly. It's much better if you initialize it near the optimum. So if what you want is the best fit values of your parameters, you're better off using an optimizer. And finally, do you expect that there will be covariances between the parameters, that changing one parameter will strongly change the likelihood of the other parameter? MCMC is really useful, as we saw, for characterizing that covariance and getting the marginalized posterior. But it can run slowly if the covariances are too strong, because you're going to end up with a lot of rejected samples if your algorithm doesn't know naturally that changing this one means that you should also change the other one at the same time. So we can reparameterize, and there will be a little bit related to this in the exercises, in order to make MCMC a better fit for this. Which MCMC code should you use? I highly recommend MC. It's probably the simplest and the most powerful for many applications. But there are more advanced versions, and so Dan is going to get more into things like PyMC3, which instead of doing a simple Metropolis Hastings or Gibbs or even affine invariant or slightly fancier versions of the sampler, you can actually take into account things like the gradient of your likelihood in order to make a very intelligent sampling. Finally, just a quick overview of things that you might want to look at to figure out whether or not your MCMC is running well. So we talked about the trace plot, which is just looking at where things are, what the value of something is at each step, and if it's getting stuck places or if it's wandering off places, that can be a good diagnostic. We also talked about the corner plot, which shows you sort of the posteriors and whether or not you're sampling your posteriors well. A couple of other related things are the acceptance fraction. So what percentage of the proposed steps get accepted and added to the chain? You want it to be around 50% or so, although it could be a bit lower. You also can look at autocorrelation between different, within your chain. So that's a way of saying how many steps do you have to go through before you get to an independent sample. And finally, there are special convergence diagnostics that also address these things. So the Gelman-Rubin statistic is something to look up for this. And how long do you run your MCMC? That's related to the previous things, but essentially, in order for your MCMC to be working, you want to have many independent samples at the end. And so you want to kind of look at the autocorrelation lengths and the convergence of your chains. Okay, I will conclude with this.
Let's do that. Actually, can we do that?
Yes.
I'm not on the microphone. Let's do this.
Okay, yeah. So a couple of other related concepts that I wanted to go through are burn-in and thinning, and these are both things that people do sometimes as post-processing. After they've generated their MCMC chain, you might burn it in, and that means that you take some number of samples from the beginning of the chain and you cut those out, and you keep only the chain after it's been running or burned in for some time. In general, burn-in is not necessary if you have started your MCMC chain in the right place. So if in this example, I dropped my chain down here near the best likelihood, there's really no burn-in necessary. It's already part of a stationary distribution where the probabilities of the probability distribution of samples that we get is the same at the beginning of the chain's run as at the end of the run. That's one of the fundamental properties of the Markov chain that we want. But if I had dropped the chain in up here, then this wasn't really a stationary distribution. This wasn't a Markov chain yet. We had to wander down here before we started getting that property. And so this chain is a case where we might want to do burn-in. And you can generally see pretty easily if you want burn-in or not just by looking at the trace. So if you were just sort of wandering around here, that's no burn-in is necessary. Like the general behavior here and the general behavior here is pretty similar. If you had something that was like that, maybe a little more randomness there, then you do want to burn in because it looks very different here from the rest of it. So burn-in can be necessary in some situations, but hopefully not in yours. Thinning is the idea that if it took us a while to get from one sample to the next, in other words, if the correlation length was long and it takes you many proposals before you get to a next accepted independent step, then you're not going to drop all of the repeated samples, but you might be able to just get away with only keeping every nth sample in the chain. And that is because you're still keeping the correct proportion of steps relative to each other, but you're not having as much repeated information in there. So thinning can be a way of, if you're delivering a chain to other people as the posterior distribution and you don't want to give them a 5 gigabyte file, then you can thin down by the correlation length. But in general, this is only dropping information. So thinning doesn't improve your results. It just might make them sort of easier to handle in the future. So, yes. All right, and then I have a few recommended resources here at the end, and the slides will be online, so you can check these out.
All right, let's thank Megan.